If not, get started soon. It's really good practice. We're doing polynomials. This is all stuff that's on the exam Thursday. So let's just review from last time. So we got standard form and factored form, and each have their advantages. Okay, so in terms of creating a graph or analyzing the function, the covariation, they each have advantages. So first of all, I've got an f function there and a g function. Which one, so you should be able to identify really quickly which one is standard form and which one is factored form. So standard form, is that f or g? Some people are saying g. It's g, okay? This is our standard form. Whoa. Try that again. Okay. All right, and then factored form. It's where it's factored. It's factored into binomials like this. Okay. So what is standard form convenient for? Do you remember?
Standard form.
Okay, n behavior.
X.
And
X-intercepts.
X-intercepts. Agree with that? N behavior and X-intercepts. Some are shaking their head. Y-intercept. Okay, so looking at this standard form here, what's true about the y-intercept? The y-intercept of a graph is where? What is the y-intercept? Where y equals 0. Agree with that? Where y equals 0, right? Right? No, it's not where y equals 0. I know it's called the y-intercept, but that's because y has some value. It's not 0. It has some value. It could be any value. It's where x is 0, right? It's where x is 0. You got to be careful. All right. So when x is 0, we can easily see what the y-intercept is here. 29. That's why standard form is easy to see the y-intercept, because it's the constant term. All the other terms will be 0 when you plug x in for 0. Okay? So that's not, if I'm drawing this one, that's not accurate. 29 up here. Okay? N behavior. How does N behavior work? What is it about standard form that helps us determine N behavior? What do we look at in the standard form? The leading term, the highest power of x. Why? Because N behavior is about as x gets very large positive and as x gets very large negative. The leading term has the most x's. So if x is a trillion, then if you multiply a trillion together 6 times, that's going to be at least a trillion times greater than every other term, because it has the most times that we're multiplying that big number together. So when x is very large, everything else is like 0 compared to it. So as x goes to infinity, what will y do, or what does the function value do for very large positive x values? Positive or negative? And as x goes to a very large negative value, what will y do? Very large negative, right? No, it's an even exponent. So you're going to multiply a negative number together an even number of times, you'll get positive. So the end behavior of this one is, whether you go to negative infinity or positive infinity, the y value will go to positive infinity. Okay? You have to analyze them. Don't memorize this. Find the leading term and analyze it every single time. Don't try to memorize, because if you don't memorize it right, then you won't get it right. But if you understand it, you can get it right every time.
So you look at it and you say, okay, if x goes to a very large number, positive.
What will that do? Will that be a very large positive or a very large negative? You see, it's very positive. If x is a very large negative number, what will that be? Still be a positive. So that's why this is saying as x goes to very see we're going this way, large negative, y will go positive. And as x gets very large positive, y will be positive. Okay, so that's, and we said the y-intercept was 29. Okay, factored form. What's factored form convenient for?
Zeros.
Zeros, also called, so zeros are like,
X-intercept.
yep, x-intercept. So zeros are actual ordered pairs. So it could be like A1, A2, etc. Okay, so zeros are when you list them as ordered pairs. The zeros are, all right, what are they? Values of x that make the function 0 or make y 0. Values of x that make y, or the output of the function, equal to 0. All right, so then roots are just those, the zeros are the ordered pairs. The roots are then just the x values, A1, A2, etc. So it's just a very small distinction. When we talk about zeros, we're talking about the ordered pairs, the actual points on the graph. When we say roots, we're calling, those are the x values. All right, and so like someone said, the zeros, so on the graph, these are the x-intercepts. Okay, but that's the key to it. That's the key. What values of x, if you put them into the function, would spit out 0? Okay? And those are the x-intercepts. Now there's one more thing we're going to cover in the second half class today, which is called the root behavior. Or what the graph is like around the roots, around the zeros. Or near, I should say near. Yeah, near or around. Okay? Together, both of these are, so standard form is primarily, you get the leading term for end behavior. Factored form, the zeros and the roots and the root behavior is called middle behavior. Meaning, what's happening in the middle of the graph when x is not super large and not super large negative. That's middle behavior. So we're going to put it all together today. But let's start by practicing just some of the stuff we did last time, just so we got it. So go to page 208. Okay, I want you to do, starting to 5, B, and D. 5, so circle as I say. 5, B, and D. And then 6, let's do also B and D. Now for 6, all you want to do is factor and find the zeros. Don't worry about graphing right now. So just we're practicing end behavior in number 5 and finding the zeros or the roots in number 6. So B and D for both of them, but don't do any graphing yet. So can we get this in 5 minutes? See if you can finish all this in 5 minutes. Work together, okay? Okay, 2 more minutes. If you're done, I'm asking another question. What's the leading term for 5C? So what's the leading term for 5C? So we'll regroup in about a minute here. What's that? Right. So how'd you do B and D? And then I just added a new question. What's the leading term for 5C? Okay, I'll just make one quick round. Grab any good question. Yeah. Yeah, so you're raising a negative number to the power of a negative number raised to an even power. leading term for gx? We're going to do end behavior. We got to make sure we got the leading term right. What is it? Yeah, so it's not always the first. Leading term means highest power, not always the first one listed. They can jumble it up. So now we're saying as x is very, very large positive, what does that thing in the red square, is it very large positive or very large negative? It's negative because x to the fourth will be positive or negative? Positive, but then we're multiplying by negative 2. Negative. As x gets very, very large negative, what will x to the fourth do? Positive or negative? That will be positive, but then we'll multiply by negative 2. Negative. So the end behavior for g, as x gets very large positive, will go to negative. And as x gets very, very large negative, g will also be negative. So here's the end behavior for this one. So I encourage you, don't look for a rule. Analyze each one separately. Because if you go for a rule, it ends up being memorization, and if you forget, then you can't do it. If you understand it, you can do it right every time. Right? What's the leading term for this one? So, what's the leading term? 7x cubed. Negative 7x cubed. Negative 7x cubed, that's right. Okay, so you don't have to FOIL the whole thing out, as we'll see for 5c. You don't want to, right? 5c, it would take you 5 or 6 minutes to get all those terms. So we just want to, all we have to do is take the biggest ones from each factor, multiply those together along with any constants, and that will be the leading term. Okay, so as x gets very, very large positive, what will negative 7x cubed do? As x gets very, very large positive, it'll be negative. Because x cubed will be positive, but we'll multiply by negative 7. All right? As x gets very, very large negative, what will x cubed be? Negative or positive? Negative. As x is a very large negative number, raised to an odd power will be negative, and then we'll multiply by negative 7. So it will be positive. So the end behavior of this one looks like, as we go out to positive infinity this way, we'll go down to negative like this. And as we go out to big, large x negatives, y will be like this. So that's the end behavior for this one. Okay, so is end behavior starting to get a little better? Is that making sense? Questions on those? So what's the leading term for 5c? So you don't have to multiply that whole thing out. You don't want it. That'd be ugly. Okay? So to get the leading term, just get the highest of each. So we're going to have x squared times another x squared. Do you see that it's x plus 3 squared? So it's going to be x squared times 3x times x. That's your leading term. So I think it's 3x to the 6th. So to analyze the end behavior, you're going to analyze 3x to the 6th on 5c. We won't, but I was just wanted you to see how that works.
We're not going to have problems with factors, do we?
Multiply that out? No.
Okay.
But that's why I'm showing you how to get the leading term without multiplying that whole thing out. Yeah. Okay, so it's for c. So you're going to have to multiply every term and every factor by every other term, and every combination, right? So to get the highest power, you're going to take the highest power from each one. So you're going to take the x squared, and then the next one will be another x squared, you see? And then a 3x, and then an x. Yeah, you got to think, what would it be like to multiply and expand every single term, and now you want the one that has the highest power? It'll be the one where you take the highest powers from each. You see that? Does it make sense? 3x to the 6th for 5c. Okay, going on to c. So we want to factor in part b. So we can first start by factoring out 2x. Make it easy. So if you got an x in every one, Take it out. We got a factor of 2, so we get x squared minus 7x plus 12. Is that right? 2x times, and then you just, this is from the old days, right? Is this x minus 4x minus 3? What are the roots? X equals 0, 4, 3. Boom. Okay, same thing here. Now we got a 2x squared, so that means we're going to have a 2x and an x. And we need to get plus 3 in here. So,
Plus 3 minus 3.
yep, so it's going to be 3 times 3, and we need to get plus 3. So we need plus 6 and minus 3, right? So this gives us the plus 6, and this gives us the minus 3. Is it right? Mm-hmm. Minus 3x plus 6x gives the plus 3x, and then minus 3 times 3 is minus 9. Zeros are x equals 3 halves, or 1 1/2, and negative 3. 2 zeros, 3 halves, and negative 3. And this one has 3 zeros. X equals 0, 4, and 3. And how those zeros, how will they help us make the graph? What will we use those numbers for to make the graph? X-intercepts, right? Those are the x-intercepts of their respective graphs. Okay, so that's all review. Are we caught up? We good? So now I want you to go on to worksheet 4. But I want to change part B. Change part B to find the end behavior. Okay? So A is good. B, change it to end behavior. Number 1. C is good. And D is good. So just do A through D and change B to find the end behavior. And then see if you can put it all together and make the graph without graphing it on the calculator. So that's kind of our goal here, is to take the equation and make a sketch of the graph without your graphing calculator. Okay, how about the zeros? What's 1, 0? Okay, so the root is 2, making the 0 2, comma 0. So we can start by graphing that point. What is there another 0? Negative 3, negative 3, 0. Okay, end behavior. So we need, for the end behavior, we need the leading term. What's the leading term? They're saying x cubed. Agree with that? Leading term's x cubed. So as x goes to positive infinity, x cubed does what? Or f will do what? It's pretty easy, right? Positive number cubed is just going to be positive. Okay, as x goes to negative infinity, we're going to cube a very large negative number. Negative. Okay, so what will we have? This and like this. Now, since there's no more zeros out here, so it's going to have to start going down to negative infinity starting at negative 3 because it's never going to come back and cross. We know that these are the only zeros or the only roots of the function. And similarly here at 2, there's no more roots out here, so from 2, that's when it's going to start going up. Okay, Y-intercept. Y-intercept is when x is 0. So you plug in 0, what'd you get? Should have gotten 12. Boom, right there. So can we piece this together now? We got the end behavior, we got the roots, we got the Y-intercept. So what's going to happen is, okay, well that's all right. We can work with that. So it's going to go up through negative 3. So now we don't necessarily know that this is the high point, okay? But there's going to be some high point around here. I don't know. It might be back here. It might be up here. We don't know that yet. So I'll just put it over here, and then it's going to come back down like this. Now, if it doesn't touch the x-axis any other place, what's the only option for this to do? It's going to kind of come down here and kiss it like this, and then like that. All right. So this is not pretty. That's why we have software, right? That's why we have the software to make a nice graph. But so we say y equals f of x, and it graphs it. And I'll do it in red. And so it should be generally like this. It's not going to be perfect, right? It's just, we got the main idea. We got the right roots, Y-intercept, and end behavior. So the question is, I'm going to get rid of this. I know how pretty it is, but I'm going to get rid of it. Okay, so now the question is, what's going on here around 2? And what's going on around negative 3, and how can we relate that to the function that was given? So this is this idea of behavior near the root, behavior near the 0. So behavior near the 0, does it look like anything familiar? Concave up, okay. But just if we were just to zoom in right there, does it look like anything familiar? Parabola. Okay, so how can we relate that to the graph? So this is the root at x equals 2. It kind of looks like a parabola. What do you see in the equation? X squared. See, so around the root of 2, that factor is squared, and we know that's x squared is our parabola. So it's like our parabola, x minus 2 squared. Okay, what about what's going on around 3? So I'm gonna try to, I guess I gotta drag it. Okay, near 3. What kind of thing is happening near 3? What does it look like now? What's that? Looks linear, right? How can we relate that to the equation, the formula? Yeah, x plus 3 to the first, right? X plus 3 to the first. So the fact that this is power 1, that's like our linear equation, x to the first. And so therefore it goes through like a linear graph. Okay, so these are called the multiplicities. The root of 2 has a multiplicity of 2. And therefore, the behavior around that root is like something squared, like a parabola. Okay? What multiplicity is this? 1. So the behavior around that is going to be like a line. Because it's like x to the first. X to the first is a linear graph. Okay, so go ahead and flip to number 2. And for C, so in A, you determine the zeros and the multiplicity of each zero. So in C, go ahead and analyze the multiplicities. Again, change C to analyze the multiplicities in terms of what the graph will be like. And then D is good, and then try to graph it E. Okay? So try doing 2, and basically just omitting C, and now we're analyzing multiplicities here. You can talk. You can work together, as always. Don't graph it on your graphing calculator. We're trying to take what we've learned and put it all together.
Oh, so then that would be 4.
So here, just right here, then we multiply this out x squared. X squared here, and this one's x to the third. Multiply these
Okay, hopefully you got most of it. The root at 3, what's the multiplicity? 2. It's the power of the factor, right? So for this root of 3, we got power 2, so that's the multiplicity. What's the multiplicity for the root of -1? 3. We'll come back to those later. What is the, let's do the y-intercept. What'd you get for the y-intercept of this? Yep, she said -4.5. That's what she should have gotten, -9/2. Okay, so we got 3 points. 3, 0, -1, 0. Those are the x-intercepts, or the root that come from the roots. And then we got the y-intercept is what you get when x is 0. Okay, end behavior. What's the leading term? -1/2 times x to the 5th. As x gets very, very large positive, what will -1/2 x to the 5th do? We'll go to negative infinity or positive infinity? Negative. So as x gets positive, x to the 5th gets positive, but you're going to multiply by -1/2. Okay? Well, I shouldn't jump the gun here. Anyway, so we know that it's going to do this. As x gets positive, y is going to get large negative. As x gets very, very large negative, what will x to the 5th do? It'll always be negative, but then we're multiplying by -1/2. So, positive. That's our end behavior. As x goes to positive infinity, f will go to negative infinity. As x goes to negative infinity, f will go to positive infinity. Okay, what's left? Root behavior. So at 3, what was the multiplicity? 2. So it'll look like parabola. But see, it's coming from below. So that parabola will be like, it will come up from below like this, and then do that. So it could go either way. It could open upward or downward. You just have to look at, I knew it opened downward because now this end behavior has to be down to negative infinity like we said, right? Okay, from here, where's it going to go? Yep. And, sorry. And I'm going to guess, and this is, you don't have to know this, but I'm going to guess that maybe that minimum is off the screen and curls back around like this and comes through like this. Somewhere that it's got to hit a low point. It's probably not going to be at the y-intercept. I'm guessing it's over here somewhere. Okay? And then it's going to come up like this. Now, what's the multiplicity at -1? 3. What's that like? It's a cubic. Do you know what a cubic looks like when it goes through the origin? What does it do? It kind of flattens out. And then that's what a cubic looks like. X cubed looks like this. Near the origin, x cubed looks like this, right? So that will be the behavior at the -1 root. But it'll be the opposite because we know it's got to be coming here from the y-intercept down here, and so then it'll flatten out and then like this, but then that matches with our end behavior over here. Okay, did you follow everything, all the reasoning I used? Did it make sense? So this is what we're thinking this graph looks like, something like this. I'll do it in blue. How do we do? We got it, okay? If I take this off, we got it. so this looks just like a parabola, x squared. This just looks like a cubic. All right, so now other way around. So let's practice here. Can we write, now we're given a graph, can we write the equation? Oh, is that the one we just did? Too close to it. Let's do something different. Let's do practice number 1. There we go. Okay, here's a good one. Can we write the equation for this? So tell me something. We'll do it as a team. Tell me something.
0, 0.
Let's start with roots. First root.
X minus
-1, 2, 0. So let's create the factors out of those roots. So what's the factor associated with the root of -1?
x plus 1.
X plus 1.
X minus 2.
X minus 2 and
X squared.
an x. Okay? Multiplicities of these factors based on what you're seeing in the graph. At x plus 1, what do you think the multiplicity is?
1.
It's linear. It's like linear. It's just going straight through like a line. Multiplicity is 1. Okay? At x minus 2,
No.
1.
There's
2. So we can get the general form of this, which would be x plus 1 to the 1, x minus 2 to the 1, and x squared. But there's a whole family of functions that have these roots and multiplicities, because we could have any factor multiplied, any number out here multiplied by this, and it would still have the same zeros and multiplicities. So the question is, how do we find that value of A?
the other point that they gave us.
Yeah, so look, it's giving you the point 1, -4. So by this point 1, -4, we can nail down what that is. So f of x equals what? -4 equals A times 1 plus 1, 1 minus 2 times 1 squared. Does it make sense? So just the roots and the multiplicities gives us an infinite number of functions based on, we could have any constant factor multiplied by those factors. But if you have a specific point on the graph, like a y-intercept or like 1, -4, we can nail down what A is. What's this A equal?
2.
So -4 equals A times 2 times -1 times 1. A is 2. Positive 2. So this would be what do we think? So let's check it with the end behavior. What's the leading term of this?
2x.
2x to the 4th, right? Leading term.
4. Yes.
2 times x times x times x squared. As x goes to positive infinity, does that go to positive infinity? As x goes to negative infinity, does that go to positive infinity? Yes. So the leading term, that works. Okay, you guys want to see? That's what I graphed. Okay, homework's, oh, shoot. I meant to pass these around. So if you want to, let's see, they are alphabetized. So if you want to come down, maybe not so many at once, but maybe in 5 at a time, you can find your homework. You do have homework due Wednesday. Don't forget web work, and don't forget your exam, most of all. Thursday's the exam. Leave the rubber band on.
Can I take the test after this class on Wednesday?
Hold on a second.